Hi, I'm Shanaz. In last lecture, we proved that if suppose we have a space X, then we proved that the space X this is simply connected if we are given any two paths with a fixed with same endpoint. Suppose we have a path F and a path G, which have fixed endpoints, say x0 and x1. So we proved that this X is simply connected if for any two paths F and G with same endpointers if they are homotopic. Now our aim is to compute the fundamental group of a circle, and in next 2 or 3 lectures we are going to compute the fundamental group of a circle, and we'll prove that the fundamental group of a circle this is isomorphic to the group of integers. But to prove this simple result we need to do a lot of homework. So first of all we will introduce the notion of covering spaces. So let us define these spaces. So let us consider two spaces. So let X and Y be topological spaces. So this is given. So we have first item here. We say an open subset. Suppose we say an open subset say V in Y is uniformly covered. This is uniformly covered if suppose we are given these maps X and Y, and say a map and P a map between X and Y. So this is given to be a map between X and Y. So this is given. So we are given two spaces X and Y and a map between them, and we say an open subset V of Y is uniformly covered if inverse image of V under P. This is the union of disjoint open sets. This is the union of disjoint open sets. Say UI, where this I is in this index set I. So for each open set V and Y, its inverse image should be this disjoint collection of open sets with an extra with this property, with the property that the restriction of P to each subset Vi is homeomorphism. The restriction of P to each subset UI. is a homeomorphism. This means that this P maps UI homeomorphically onto V, i.e. P maps UI homeomorphically onto V. So in this case we say this P uniformly covers this V, i.e. V is said to be uniformly covered by P. Now second item is that we say the map P from X to Y is a covering, and the space X is said to be a covering space of Y, and in the space X is a covering space of Y if first condition is that if P is surjective, and for each and for every Y in Y, for every point Y in Y, there exists an open neighborhood V of Y which is uniformly covered. There exists an open neighborhood of Y which is uniformly covered. So this is the definition. Now what do we mean by this uniformly covered? So we say a subset V of Y. So suppose this is space X and this is space Y. Suppose this is the map P, and we say this X, this is a covering space of Y if first of all this P is a surjection. And suppose we are given a point, say Y in Y. Suppose this is an open neighborhood. Suppose this V is an open neighborhood of Y. Now for each point Y in Y, this open neighborhood, this must be uniformly covered by P. That is, for this P, this P inverse P V, this is actually the collection of open sets UI. Now these open sets UI, they are in X. So this P inverse V is open set of is the collection of open sets of X, such that when we restrict P to UI, we get this V, and this is homeomorphism. So this is homeomorphically. So this P maps UI homeomorphically onto V. So in that case, this P is said to be covering map, and this X is said to be covering space of Y. So let us do some examples here. So one should note first, we had the following remark. So if V is uniformly covered subset of Y, then any open subset of V is also uniformly covered. So if V is uniformly covered, subset of y. And this means then clearly any open subset of V is also uniformly covered. So let us do examples now. This is example first. So let us take let over X be the space of real numbers and this Y be the circle S1. Now consider a map so let us consider the map P from R to S1 such given as this P takes this X to e to the power ix. Obviously this X is a real number and this e to the power ix, this is some number, some point on the circle. Then we claim that this P is a covering. Then P is a covering. For example, so to prove P is a covering, first of all, by definition of this P is surjective. P is given to be surjective because for each real number, for each point on the circle S, there is some real number X such that P of X is that point on the circle. Now let us consider a point, say y is equal to, so let y is equal to say a point I alpha. Let us take this point in this space S1. Now let us consider an open neighborhood of this point y in S1. So be a point. Now what we do, we pick an open neighborhood of this point y. We pick an open neighborhood of y in S1. Let us note that neighborhood by V. So this V is given as, so it contains all those points ix such that this x, say suppose this is in the interval alpha minus pi by 4 and alpha plus pi by 4. Suppose we have circle here, the circle S1, and suppose this is our point y, which is equal to e power I alpha. Now we are taking this open arc, so this is our V. Now let us see what is the inverse of this V. Then P inverse V. Now this P inverse V is this disjoint union. So this is the notation for the disjoint union of these open intervals. So alpha minus say pi by 4 plus 2 pi j and alpha plus pi by 4 plus 2 pi j, where this j is an integer. So note that for this interval we have some interval over here, which and that interval is mapped to this open arc. Now when we translate this open interval in R by this period here, we translate this open interval here. So what we do, we take a full round of this circle here and we reach again to this point. So that means this interval is again mapped to this interval. So this is same as union J in Z of UJs, where this UJ is this open interval alpha minus pi by 4 plus 2 pi j and alpha plus pi by 4 plus 2 pi j. So one can see here, if we restrict p over this uj, what do we get? We get this interval over here. So which is union of disjoint status. Also the restriction of P to say uj is a homeomorphism onto V, because if we take image of, if we look at image of uj under this map P, we get this V back here. So what is actually happening? So we have this real line here, and suppose this is over alpha. Now this is over open interval alpha minus pi by 4. Let us do this. So this is our circle S1. So we take a point here which is e to the power I alpha, and we take an open neighborhood of this point. So this is our point Y. We take an open neighborhood, so this is S1 here, this is R here. We take an open neighborhood of this point, which is over V. Now the inverse image of this V is these intervals. So this is U0, here U1, here U minus 1. So these all UIs are mapped homeomorphically onto this set V here. So these are open intervals which are at a difference of 2 pi times some integer. So they are translations of the same interval which are at a difference of 2 pi. So any two consecutive intervals, they are at a difference of 2 pi. Now one can look at this map. So we can look at this map P from R to S1, which is given as so this S goes to e to the power is. So if one can wish, we can take this as the real coordinates, cos of s, sine of s. So these are the points on the unit circle, on the unit circle. So this can be visualized geometrically by embedding. So we have to embed r into r3 as the helix. So if we embed this r in r3 as a helix, parameterized by, that means that this s goes to say cos s, sine s, and s. So this is the parameterization of circle. So one can embed this r into this r3, and this is the given parameterization. So now we have this space x here, this is our space x here as this helix. So this is our real line r embedded in r3. This is our space x. Obviously this helix, this is homeomorphic to the set r of real numbers. So this is the homeomorphism here. Also let us take this circle here. So this is over s1. So this is s1. So this is our point, say y. So let us pick another color here. So this is point y is equal to e I alpha, and we take this open neighborhood of this y. So this is our open neighborhood of y, which is v. Now this is our map P. Now the inverse image of this v over here is this segment here, this segment here, this segment here, this segment here, and so on. So these are disjoint union of open sets. So now what this P does here, this P behaves, P is the restriction to the helix of the projection of R3 onto R, that is. So let us write this over here. So one can so the map, this can be visualized geometrically by embedding this R in R3 as a helix, which is parameterized by this S goes to this triplet here, and this P in that case is, this P is the restriction to the helix of the projection of R3 onto R, of the projection of R3 onto R. So this projection is given as, so this x, y, z, which is a point on a helix. This is mapped to, so this is our P here, this is mapped to point x, y. So actually what we are doing, we are collapsing this spiral to this circle, and during this collision, during this collapsing, these segments, these all segments, they are identified with this open set here. So these, suppose this is our u0, this is u1, this is u2, this is u minus 1, and so on, like that. Let us consider another example. So this is example second. Let us take x to be the infinite helix. So let us take x be the infinite helix. That is, this x is actually this triplet here, r cos theta, r sin theta, and this theta here, where this r is between 1 and 2 and theta is a real number. And consider this y to be the annulus and y to be the annulus. So this y is r cos theta, r sin theta, where 1 is less than r is less than theta, sorry 2, and theta is a real number. So again we have this helix here. So let us draw this helix here. So suppose this is our helix here, so just like this. So just like this. Let us make this a little bigger. And again it goes on and on. So actually my drawing is not that much good. So this is our this infinite helix. So it goes on like this. So this is over h. So this is over x. So this is over x over infinite helix, that is r e I theta and theta, where this 1 is less than r is less than 2 and this theta is a real number. Now this infinite helix, this is the covering space of this annulus here. So we have this annulus here. So this is over y, which is r e I theta, why this 1 is less than r is less than 2 and this theta is a real number. Now if we consider a point here and take an open set around this point here, now this is our map P. Now the inverse image of this map P is an open set here, an open set here, an open set here, and so on. So this serves as an covering space of this space Y here. Now let us give an example of a map which is not a covering. So this example third. So take this X to be the unit circle, say S1, and this Y to be the interval -1 and 1, and let P be a map from X to this circle S1 to the unit and to this interval -1 and 1, defined as, so it takes this pair XY to the point X. So actually this is the projection on the x-axis, projection. So clearly P is not covering space. Clearly P is not a covering, since this X is not a covering space of Y, because let us show why this is not a covering space of Y. So clearly P is not a covering, because we know for each point in this set one must have an open neighborhood that is uniformly covered. So clearly P is not covering, since the point Y is equal to 1 in this interval 1 -1 comma 1 has no open neighborhood, has no open neighborhood which is uniformly covered, which is uniformly covered. Now here is a lemma which states that, so let P from X to Y be a covering of a topological space, say be a covering of these topological spaces. So if Y is path connected space, if Y is path connected, then for any two points, say y1 and y2 in Y, the size of this set, so this is this set P inverse y1, this is, and this has many pre-images, or this is at least one pre-image because P is surjective. So the size of this set and the size of this set P inverse y2, this is same. But for a general map P between two spaces, the number of pre-images of a point is depends of course on the point chosen in space Y. So let us make this remark here. So for a general map, say P from X to Y between topological spaces, the number of pre-images, the number of pre-images of a point depends on the point chosen in Y. On the point chosen in Y. For instance, if we look at the previous example where the space X was over unit circle, say, so this is over unit circle S1, and over Y was this interval -1 1. So this is the point 0 1 here, this is the point 0 -1, this is the point 1 0, and this is the point -1 0. So if we look at this example, so this is over P where this X Y, this is mapped to, this is mapped to X, so this is the projection map here. So we seen in the previous example that this P is not a covering map. So one can also observe here, now these two spaces, they are path connected. Had this map been a covering map, then one would have P of 0 equal to P of 1. So the sizes of these two sets would have been equal. But one can see over here the inverse image of, sorry, this is inverse image. The inverse image of 0 is this set 0 1 and 0 -1. So its size is 2. However, inverse image of 1, so these 2 points are mapped to 0, this point is mapped to 1, this point is mapped to -1. So inverse image of this 0 over here is these 2 points. In fact, other than these 2 pointers, inverse image of any point consists of 2 points here, because so P inverse -1 is this set 1 0, which is singleton. So this is not equal here. So this is not a covering.